Hi everyone, my name is Wendy and I'm an incoming fourth year undergraduate at the University of California, Merced, studying computer science and engineering. Today I'll be presenting my project Improving Water Supply Forecast via data-driven rain-snow partitioning in hydrology models. Rain-snow partitioning is a process of determining at any given point in time whether the precipitation falling from the atmosphere is rain or snow. This is highly important for managing water resources. Hydrology models, which are used by irrigation districts and state water management agencies, are crucial for forecasting water availability, but simulating rain poses challenges which impacts water availability accuracy. Rain-snow partitioning is an important factor because it determines the appropriate precipitation threshold. By knowing if precipitation is rain that directly contributes to stream flow or snow that will eventually contribute to stream flow upon melting, will allow irrigation districts and state water management agencies develop better drought management and planning. The objective of my project was given precipitation values at any given point in time along with other environmental variables, determine whether precipitation is in the form of rain or snow. Since this was my first experience with machine learning, I started with basic machine learning applications. I then compared these applications to an existing benchmark, which was a study conducted in 2018, and the environmental variables I worked with were surface air temperature, relative humidity, and surface pressure. These environmental variables also served as the input variables to my model. This flowchart depicts the process I took to develop my model. So starting off, we have my input data, which was a global data set of precipitation phase and environmental variables. I then filtered the data set to only include data points within the -3 to 5 degrees Celsius temperature range. And the reason why I did this is because within this specific temperature range, precipitation can fall as either rain or snow depending on specific atmospheric conditions. I then took a random subset of the filter data set and created three data tables, each of which had a different combination of the environmental variables or input variables to the model. The first data table considered air temperature, the second considered air temperature and relative humidity, and the third considered air temperature, relative humidity, and surface pressure. Afterwards, I split each of these data tables into a 70% training set and a 30% testing set. And I utilized the carrot package in R to train multiple classification models. And the 6 classification models that I used are listed here in case you're interested. Then I merged the predictions of the models to create a combined prediction using the ensemble model. And finally, using that same ensemble model, I made predictions on the testing data. These three box plots showcase the accuracy of the individual machine learning models I considered for each of the different combinations of input variables. Within each of these box plots, the accuracy of the individual models did not differ significantly, which led me to use an ensemble model, allowing me to combine multiple models to improve prediction accuracy by leveraging the strengths of the different models and minimizing their weaknesses. This allowed for more robust and accurate predictions. The results of the research project indicate that there was no significant accuracy improvement in basic machine learning models compared to the binary logistic regression model that was used in the benchmark. Due to time and this being my first experience with machine learning, I was only able to test out 6 models and did not get a chance to tune hyperparameters. These plots showcase the accuracy rates of the current project in orange bars compared to the accuracy rates of the benchmark in blue bars for each of the combination of input variables. So as you can see, the ensemble model of the current project did not achieve higher accuracy rates than the benchmark. Also, the plot illustrates that there isn't a huge difference between the accuracy rates of the 3 different combinations of environmental variables. So for instance, if you take a look at the plot for temperature and relative humidity, For the benchmark specifically, we have 91.5% accuracy rate compared to the accuracy rate of the temperature, relative humidity, and pressure, where the benchmark accuracy rate is 91.4%. So there isn't a huge difference between the accuracy rates. The next step of this project is to build an improved model. I would do this by exploring additional models and fine-tuning various hyperparameters to potentially increase accuracy. Some personal takeaways of this internship was that I was able to gain valuable experience in applying machine learning algorithms to real-world datasets in R, as well as gain hands-on experience with QGIS for spatial analysis. Overall, I developed a foundation for future research and projects involving machine learning and spatial analysis. I want to give a huge thank you to my mentors, Boopy and Kirti, for providing guidance and support throughout the summer, and a special thank you to the Agate Institute for giving me this opportunity to come out to Pullman to be a part of this project. Here is my contact information if you would like to connect, and thank you so much for listening to my presentation.